In this lecture, we are going to talk about image description, in particular color and texture. In the previous lecture, we already have seen what is the meaning of color for digital images. So I'm going to give you a brief introduction about how to describe color in images so that we can compare images in terms of their color content. And also, I'm going to introduce the concept of texture in terms of digital images. So first, about color. Usually, when we want to describe an image in terms of its colors, what we do is to use a feature vector that is computed using the histogram of all intensity values of the image. If the image is a gray level, or we can compute the histogram of all colors in terms of the channels RGB. We can also use different color spaces and also make a fusion of the RGB channels into one channel that codifies the colors that we want to describe. So the simplest way to do that is to use what we call a global color histogram. This computes a single histogram for the entire image using the frequency values as descriptor. So this is basically just a regular histogram, however, usually normalized in order to sum up to 1 or for its maximum value to be 1. But this first descriptor here, although it can work in some simple cases, is often not very good as a general descriptor. So we can use instead the method called border interior classification. In this method, we compute two histograms. And those two histograms will be dedicated to different pixels. So one histogram will count only colors for pixels that are considered to be interior. What this means is that the pixel have all neighbors with the same color of the central pixel. This means that that pixel is probably in a flat region. So if it's not interior pixel, so if it's not lying in a position in which all its neighbors have the same color of the central pixel, it is considered as a border pixel. So this splits the histogram, the color histogram, into colors that happen in flat regions and colors that happen in texture or high variance or border regions of the image. Those methods will generate a vector of values. So for example, a histogram, an RGB histogram, if we compute it separately into those three channels, if we use just the regular histogram, what we have is 3 times 256 values. So this will be the vector that will describe the image. And this can be really high in dimensionality. That's why often we make a fusion of all channels, or we requantize the image. So we instead of using all the 8 bits, we can use, for example, we can normalize the image in order to for the values to not be in between 0 and 255, but for example in between 0 and 63, which is a well-known parameter value. So we have 64 different colors only, either for each channel RGB or for a combination of them. And also it is noteworthy that when we talk about descriptors, we often mean that we have a pair of feature vector and distance function that allows to compute the similarity between two vectors. So in this case, two vectors that represent images. I'm going to comment about two distance functions that are widely used in the case of color descriptors. There are the Euclidean distance that captures circular or radial relationships between vectors. That it is the well-known L2 norm as well. So we just compute the difference, square them, sum them all, and take the square root. But also the log distance can be used. The log distance is a variation of the L1 norm distance. However, it computes a logarithm in every value of the histogram. Why is that? Because the log will diminish the values that are the influence of the values that are too large. So for instance, if we have an image with a constant background, so let's say this light here that is mostly white, if I apply the log function, what happens is that the white will not influence that much will not dominate the distance. And because of that, because of the log function, we often normalize. If we want to use the log distance, we have to normalize the histograms, not to sum up to 1, but instead to a value that is a power of 2. For example, 1024, 512, or 256. In terms of texture, we have a more complex scenario, because for us humans, it is not a direct vision system. It is often related to a tactile or haptic perception. This texture is often something that relates to surfaces or to objects in terms of its roughness or smoothness. In images, texture is a concept related to local differences in the intensity levels, in which the most important elements to differentiate them are the difference in the pixel levels, so the contrast between them, the size of regions to be considered, so the window that we are taking, the direction or lack of direction of those intensities. So let us take this image as an example. We can consider this image to have a kind of texture in terms of the local repeated patterns. And in this case, I take this rose as a pattern that repeats in a field of roses. We also have other elements here, but in this case, the texture that I want to describe or that I want to focus on is that rose or the tulip. So we have two main characteristics for texture. The first one is a repetition of a given pattern. So for example, oval patterns, just by repeating them, we have a kind of texture here. We can also have a stochastic behavior of texture, so that means there are differences in the pixel levels. However, they do not occur or they not repeat in a well-behaved way. It is random. And we can have both of them as well. So in this case, the tiles repeat, but the values inside the tiles can be random or stochastic. Or the rocks can also repeat, but inside each rock we have a distinct stochastic nature of pixel level change. So this kind of analysis will allows us to compare texture and look for similar or different patterns. If we try to do that by only using the distance between every pixel pair, we are probably going to fail. So we have two patterns here that are the same in terms of texture, but computing individual pixel differences, it's not a good idea. So we have two basic approaches. The structural one that goes top down, so it decomposes image in basic elements or primitives. So we are working with very, very basic elements that we call texture elements or texels. This is adequate for artificial texture or for well-behaved patterns. So for example, we have a single primitive here that says that the texture that I want to look for or that I want to analyze or create is a checkerboard of 6 by 6 values, and it's a binary one, so it changes from 0 to 1 or from 0 to 255. In the right hand side I have a stripe or a horizontal stripe in the same sense. So this can be useful, but it can be limiting in terms of natural images, as I'm going to mention. So we can have instead a statistical approach that is also called bottom-up, that characterizes texture as a series of statistical properties in a small group of pixels. It is often adequate for natural texture. So in the case of the structural texture, we can have primitives, for example, a checkerboard or stripes or a star pattern, and we consider that every region is uniform in terms of the average value, the contrast, the flat regions, and so on and so forth. So the granularity of the texture is given by the size of the primitive. I could, for example, select a checkerboard pattern with just 3 by 3 pixels or with 6 by 6 pixels. And we can also have the same textile organized in different structures, or same structures with different textiles as well. In these lectures, I'm going to focus on the statistical approach. This is because defining segment regions of textiles can be a challenge if you want to do that by hand. So texture would look similar, but it's hard to extract their really structure. So in this case, for example, we have those flowers, and it is hard to really spot and design their specific orientation, and so that I can design them using a structural approach. So instead, I'm going to use statistics to compare them. So I can use numerical or statistical measures to describe texture to be computed either in gray level or color. We often compute it in a single channel, for example, by converting an RGB image into grayscale by some mean. The first, I talked about color and its most simple way to describe, which are histogram-based approaches. And in the case of texture, the most basic approaches uses statistical measures. So the first four statistical moments are widely used, such as the mean, the standard deviation, the skewness, and the kurtosis. So those are widely used, but also other measures such as the uniformity and the entropy are also widely used. So we can fix then a region of pixels. So for example, a window of size 5 by 5 or 9 by 9 and so on. And then inside that region, considering only those pixels, we can compute, for example, the four first statistical moments, the uniformity and the entropy. So because the uniformity and entropy are less common, I'm going to describe them. So let Z represent indices of pixels in a given window. So P of Zi means that we are taking the value of a normalized histogram of a given intensity Z of I. So Z of I is the intensity, is the intensity that I want to work with. So this P of Z of I is the frequency of some intensity Z of I, in which P is a normalized histogram. So the uniformity basically computes the square, basically squares all the histogram values and sum them all. And the entropy will compute the histogram for each element of the histogram inside a region, and then sum them and invert the sign. This is because when we work with normalized histogram, we mean that the maximum value is often 1, so it will log of something in between 0 and 1 will cause the output to be negative. So I just invert it.